Okay, in this next section, we're going to talk a little bit about patterns and algebra and how they're related to the work that we do in elementary school teaching. You may think to yourself, wait a second, algebra is not something we do until high school, but algebraic thinking is something that we do even in the earliest of elementary grades. We're going to talk a little bit about growing patterns and trying to connect the types of things that children can do with these growing patterns to where they all go by the time we get to Algebra 1. So, math in general is the study of patterns. We examine patterns within numbers as well as geometric objects. We use patterns when we are trying to generalize procedures and new algorithms, like you'll see a little bit later in the semester. So it's important that students from pre-K all the way through 12th grade are able to identify the structure of a pattern and see how it's changing, to be able to extend the pattern and to apply the structure in order to systematically collect and organize data, and then to use this data in order to generalize the pattern. This is very similar to what we did in the clinking glasses problem, where we looked at different examples, collected data, organized that data, and then used that to extend the pattern and then eventually to generalize that pattern into that n times n minus 1 all divided by 2 rule. If we look at the pattern below, star, star, ampersand, star, star, ampersand, star, and we ask what the next three terms in the pattern would be, well, if I look at the pattern, it seems that this part right here is the part that repeats. So star, star, ampersand, star, star, ampersand, star. So we should have star, ampersand, star. And if I were to describe this pattern in words, one of the ways that we do this with children is we look at the fact that in this block, this is the repeating block, there are two elements. We'll call this first element A and the second element B. And if I think about the way that this pattern works, this is what we call an A-A-B pattern. A-A-B, 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 A, and so on. It doesn't matter what these symbols are that represent A or B. In this case, these are the stars and the ampersand. But what we really have, I mean, this could be stomp, stomp, clap, stomp, stomp, clap, stomp, stomp, clap. It could be anything. It could be red, red, blue, red, red, blue, circle, circle, triangle, circle, circle, triangle. Any of these are what we would call AAB patterns. And we can use those letters, naming the individual elements of the blocks, to describe a bunch of different repeating patterns. So we can have an AB pattern, an AAB pattern, ABB pattern, ABBA, all these things. When we look here, we're going to look at Lab 2, looking at patterns, not repeating patterns in this case, but growing patterns, and how they're related to the things that we think about algebraically. There are 4 tasks on the lab. We're going to do 2 of them together, and then I'm going to leave the last 2 for you to complete. And then you'll scan it and submit it and all that good stuff. So we're going to work through 2 of these tasks on Lab 2. We're going to do the sticker cubes and Mary's cookies. Then you're going to, as I said, complete the remaining 2 tasks and then submit a completed scan of the lab. So you may want to pause for a second before you move on. You want to make sure you print out Lab 2 from Canvas. So the tasks that we're going to work on together, you can complete as we work on them together. And then you can go ahead and finish the other 2 here at the end of this lecture. Okay, so the first task we're going to talk about here in Lab 2 is something called sticker cubes. And again, this is going to be an example of what we call a growing pattern. So here's our task. A company makes colored rods by joining cubes in a row and using a sticker machine to put smiley stickers on the rods. The machine places exactly 1 sticker on each exposed face of each cube. Every exposed face of each cube has to have a sticker. This rod of length 2, which is made out of 2 cubes, would need 10 stickers. Now we can't quite see them all, but I know that there is 1 here, 2 here, 3 here, 4 here. These 2 on the top, there's also 2 on the bottom, 5 and 6. These front faces also have back faces, 7 and 8. And then I have this side, 9, and then I have this other side, 10. So, as we said, a 2 rod would need 10 stickers. What I'd like you to figure out is how many stickers you would need for a rod of 3 cubes, for a rod of 4 cubes, for a rod of 10 cubes, and then I'm going to ask you to see if you can generalize a rule for any given number of rod. And then we're going to say, how does our rule connect to the way that we counted stickers on the cubes? So for example, that last question ties back to what we said in the clinking glasses problem. So when our rule was n times n minus 1 over 2, if the question said, well, how does the rule connect to the way you counted the glass clinks? We know that n represented the number of people at the table, and each of the n people clinked glasses with everybody except themselves. So one less than the total number of people who were at the table. That's what n minus 1 was. So n groups of n minus 1. And then we talked about the fact that we actually, when we count that way, we double count. So we have to divide by 2. So I'd like you to be able to connect your algebraic or symbolic rule to the way that you count those stickers. And that will become a little bit more obvious as we do a few more of these. So let's take a look at some ways that we might look at exploring this problem. So the easiest way for me to think about the sticker problem is to draw some pictures. So I'm going to start with the 2 cube that we had. Draw it in 3 dimensions here. Be a little bit better than that. I'm drawing it a little bit different than the original picture, but I know that there is a smiley face here, 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 this side. Again, so 1, 2, 1, 2, 3, 4, 5. These are the 5 faces I can see. There's 5 other faces that I can't see. There's 1 over here, there's 2 on the bottom, and then there's 2 in the back here. So there's 1 here, and then 2 here, and then 2 here. And so I can see that altogether I'm going to have 10. Undo those just for a sec. So what I'm going to do now with this 2 rod, I'll make a little table over here. So number of cubes and number of stickers. So when I have a 2 rod, I know that I have 10. If I think about a 1 rod, that's just a single cube. It'll have 6 sides, so it'll have 6 stickers. So when I go to do my third, what I'm going to do is I'm going to draw in a different color here, and I'm going to just think about what would happen if I put another cube here. So this blue one I'm going to put right here. And I'm going to think about what would happen. Well, this front face would have a cube. This top face would have a cube. So these are the 2 faces I can see. I know there's a bottom that will have a cube, and I know that there's one opposite of that one that will have a cube, and then this will have a cube. So it looks like I would have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 faces that I could see, which means there's going to be 7 faces that I can't see. So when there were 3, I'm going to have 14. And if I drew my 4th cube, one of the ways that I could look at this is that I would have a sticker here, and then a sticker there. If I counted these 1, 2, 3, 4, 5, 6, 7, 8, 9 faces I could see, plus 9 faces I can't see. That means if I had 4, I would have 18 stickers. So I have 3 and I have 4. That's what they want me to find. They also want me to go all the way to 10. Maybe at this point what I want to do is look at my table a little bit closer and see if I can get it to 10, and then if I can see if I can find a closed formula. We've seen our drawings, we've generated a table, and now what we're going to do is take a look at our table. So at this point, my table goes all the way through 10. I want to kind of focus on this area here. We know that when there is one sticker, or excuse me, one rod, there are 6 faces. We saw from our example when there were 2 rods, there were 10 stickers, 10 faces. 5 we could see, 5 we couldn't see. When we added our third rod, our third cube on the rod, we had 14 stickers. And when we had 4, we had 18 stickers. And if I go ahead and I take a look at, and I add these on here, what I want to look at is the change between consecutive entries. So, for example, when the rod length goes up 1, the number of stickers seems to go up by 4. When the rod length goes up by 1, the number of stickers goes up by 4. When the rod length goes up 1, the number of stickers goes up by 4. This change that we're talking about, these 4s over here, between consecutive entries are what we call the first order differences of the pattern. The first order differences can help us identify the recursive formula in the table. So we know that if we know, if we understand that when there are 2 cubes in the rod that there are 10 stickers, and we know that every time we increase the rod length by 1, the number of stickers is going to increase by 4, we know that we can continue generating numbers for this table. So even though we only kind of got to here, if we keep adding 4 stickers every time we increase the rod length by 1, we can use this to get all the way down to 10 to find that there are indeed 42 stickers on a rod that has 10 cubes in it. So when we think about the recursive formula, as the rod length increases by 1, the number of stickers increases by 4. We sometimes call this a first next pattern, or a first next rule, because if I know the first entry, I can find the next entry by doing something, in this case adding 4. What we're also trying to figure out, though, is what happens from 4 to 18. What happens to get from 3 to 14? That closed formula like we looked at in clinking glasses. Well, one of the ways to help us figure out what this is to back up this pattern one more and actually figure out what happens when there are no rods. Now, this doesn't make a lot of sense, but if there were 0 cubes in the rod and I back this up to see what happens above it, you can see if I go above, I'm subtracting 4 every time, right? 18 minus 4 is 14, 14 minus 4 is 10, 10 minus 4 is 6, and that means that the one that comes before 6, so if there were no cubes, it would be 2. Knowing that when there is 0 rods, 0 cubes, that there's going to be 2 stickers can help us think about what's going on here. Because what that tells me is no matter what I'm going to multiply the rod length by, I have to add 2. So I can really think about what happens if I've already added 2. So if I've added 2 to get 6, then before I added 2, there's like a 4 here. And before I've added 2, this is really 8. And before I've added 2, this is really 12. Well, now if I think 1 changes to 4, 2 changes to 8, 3 changes to 12, 4 changes to 16, I can actually see that my explicit formula for this should be multiply by 4 and then add 2. So if it's n, this would be 4n plus 2. The second task we're going to look at is a reverse pattern problem. So in this case, I've given you some of the inputs and some of the outputs, and we're going to use that to generalize our recursive formula and our closed formula. So this is Mary's cookies. Mary had a table with the prices for boxes of Girl Scout cookies, but it rained and some numbers were wiped out. Uh-oh. Let's help Mary fill out her table. So we want to see if we can find the recursive formula, and we want to see if then we can find a general rule using n for the pattern. Now, you can see when we look at this that we have some of the data, but we don't have some of the data. But if I looked here, just at these first three things, one of the things I can see is that as the box of cookies goes up 1, the price for the cookies goes up 3. And when the box of cookies go from 2 to 3, the price goes from 6 to 9. That's up 3. So it looks like my recursive formula is every time the boxes go up 1, the amount of cookies goes up 3. So with that in mind, I should be able to figure out that with 4 boxes of cookies there is 12. 5 is 15. 6 should give me 18. 7 is 21. 8 should give me 24. And 9 should give me 27. 10 we know is 30. And here we can kind of see that closed formula should be 3 times whatever n is. Right? 1 times 3, 2 times 3, 3 times 3, 4 times 3. And just to be sure, if we went up to no boxes of cookies and we subtracted 3 as we moved up, right? 12 minus 3 is 9, 9 minus 3 is 6, 6 minus 3 is 3, 3 minus 3 would be 0. That tells us we're not going to add anything. No addition, no subtraction. And you can see when we look at our rule, it's just take the number of boxes of cookies and multiply it by 3. So now what's going to happen is you're going to finish the other two tasks. They're very similar to the ones that we just talked about. The first one you're going to do is another growing pattern. It's like the sticker cube problem. It's a little bit different, but this is called trapezoid tables. Mrs. Chen decided she would place the chairs around each table so that 2 chairs will go on the long side of the trapezoid, here, and then 1 chair on every other side, so here, here, and here. This way, 5 seats fit around 1 table. And if she puts 2 tables together like this, she sees that 8 seats, 1, 2, 3, 4, 5, 6, 7, 8 seats can fit around 2 tables. What I'd like you to find out is how many seats can fit around 3 tables? How many seats can fit around 10 tables? Can we generalize a rule for any given number of tables? And then how does our rule connect to the way we counted seats at the table? You can see this is very similar to how we approached the sticker cube problem. And similarly, another reverse pattern problem, this is the paddleboat problem. Now this one's a little bit different. I have less numbers that I've given you here, but the same idea will work. Susan is renting a paddleboat. It costs $1.50 to rent a life vest, and it is $6 an hour to rent the boat. Below is a table of the total cost for one person to use the paddleboat safely. Can you fill in the missing values? Then can you find a recursive formula? Then can you write a general rule using n for the pattern? So, ideally you have completed the 2 problems we already did, the sticker cube problem and Mary's cookies. What I'd like you to do now is to complete the remaining 2 problems. Again, show your work as much as possible, briefly explain your process, make sure your final answers are identified. When you finish, scan and submit the lab to Canvas. Please label your file as your last name _ lab 2. So if I were submitting it, it would be Tominski _ lab 2. Okay, good luck.